Okay, so now I'm going to be talking about a set that is orthogonal and normal. Orthogonal means dot product is 0. Normal means of length 1, right? That's what the unit vector was. So if I have this set here, this subspace W that's spanned by this set of vectors, if W is a subspace spanned by a set, by such a set, okay, by like this set of p vectors, then it will, these set of p vectors will be an orthonormal basis that is automatically independent. Let's see, if W is the subspace spanned by such a set, by this orthonormal set, then this, if this is orthogonal of length 1, orthogonal, they will be a basis because they're linearly independent and will span. All right, so let's talk about determine which of these sets are orthonormal, and if the set is only orthogonal, then normalize it. Make the vectors of length 1. So let's just check this set of vectors out and see if it's orthogonal. So I do the dot product, I get 0 plus, 0 minus 1, oops, I can't erase here, 0 minus 1 plus 0, so this is equal to -1, so this is not orthogonal, so it's not even possible to make them of length 1. So not going to worry about it, not orthogonal. So because it said if it's orthogonal, then normalize. Okay, so let's do this one. So -0.6, 0.8, 0.8, 0.6. So I get, this does give me -0.48 plus 0.48. This gives me 0. So they are orthogonal. Okay, so now let's check out what, let's just call this the vector u and this the vector v. Let's check out the length of the vector u. Plus 0.8 squared. That would give me, oh, look at that, it gives me 1. And the same thing for this. This gives me a length 1. So this is an orthonormal set or basis already, right? Orthonormal basis because they're an orthogonal set and they're of length 1. Okay, so let's do this. So if I take and do the dot product, right? 1/3, 1/3, 1/3, -1/2, 0, 1/2. If I do the dot product, that gives me 0. So they are, in fact, orthogonal. Okay, so now let's go find out, if I call this u and this one v, let's go find out the length of u. So the length of u will be 1/9 plus 1/9 plus 1/9. So it'll be the square root of 3/9 or root 3 over, root 3 over 3, what I meant to say, or let me just rewrite it as 1 over root 3. Okay, if I wanted to find the length of v, that would be the square root of 1/4 plus 1/4, so 2/4, or root 2 over 4, or I'm just going to rewrite it as 1 over root 2. Okay, so if I want to find the vector of length 1, that's going to make the orthogonal or normalized set, I'm going to be taking 1 over root 3 times this vector. 1 over the length times this vector. 1 over this times this gives me root 3 times this vector. Okay, and then if I'm going to take the normalized vector from this, I'm going to take 1 over this times this. So 1 over this times this gives me root 2 times this vector. So this would be the normalized set. All right, so let's talk about this orthogonal projection. All right, so first off, I've got this non-zero vector u in Rn. So here's u, happy u down here. And y is a vector that's in Rn also, but it is not in the span of u. So y is not in the span of u. Okay, so y is not down here. Y is somewhere like here. Okay, all right. So what I want to do is I want to do a projection. So I literally think of a sun. I know, like the literal sunshine, the projection being the shadow of the vector y onto the vector u. So the shadow, let me see if I got a different color here. I think I do. Okay, so this right here is going to be called y hat. So y hat is the projection of y onto u. The projection of y onto u. So let me go back to black here. Okay, so then what I'm going to do, so this is y hat here. So then what I'm going to do is I'm going to find this new vector that's called z, and z will be the orthogonal vector. So let me see if I get another different color. This will be my vector z. And z is orthogonal to u. And how I find z is I take this vector y, take this vector y hat here, take this vector y hat, and so this is y hat here to here, right? I'm going to take this tip and put it here and subtract it and move it over here. So this is my y hat. So let me go back to black. So what my z vector is y minus y hat. Whoops, y hat. That's supposed to be a y hat. So there it is. So z, this green vector z, is this vector y with this tail to tip, subtract off y hat, and that's how I get this orthogonal vector z. And so I'm going to be interested in, so the orthogonal projection of y onto u is this y hat, finding that first. So that's what you always find first. And then you have the power to go find out what z is, which is the orthogonal vector to it. All right, so let's go use it over here. So you do not have to draw a picture every time, but I think that helps to understand what you're doing. Okay, so I just wrote the formulas up here again, so you knew what you were doing. So finding z, which is y minus y hat, but the first step is always finding y hat. Then you can go find the z. So here's your vector y, and here's your vector u. So you can see that y is not in the span of u. Good. All right, so let's go find y hat. So y hat will be y, which is 2, 3, dotted with u, all over u, whoops, dotted with itself, times the vector u, which is 4, negative 7. So I get 8 minus 21 over 16 plus 49. All times the vector 4, negative 7. Oops, negative 7. Okay, so 8 minus 21, that gives me a negative 13 over a 65 for negative 7. So that gives me a negative 1/5 times 4, negative 7. Okay, so I'm just going to combine that to be y hat is going to be negative 4/5 times a positive 7/5. So that's my orthogonal projection of y onto u. So now let's go find z. So that's the first step, right? Finding z is the second step because they want me to find two orthogonal vectors. So finding z, so z by definition is y subtract y hat. So the original vector y, y, subtract y hat. Okay, so I'm going to go really slow so I don't make any mistakes because this potential is huge, right? So I have 2 plus this, right? So 2 written as 10/5, right? Plus 4/5. Then 3 minus 7/5. So I'll say 15/5 minus 7/5, right? So I get 14/5 and 8/5 here. So that's my vector z. Okay, so the bottom line to answer the question, write y as the sum of two vectors, y hat plus z. So it always should work, right? So y hat we found was negative 4/5, 7/5. And my z vector is 14/5 and 8/5. So let's just make sure that works to equal what y is equal to. So y was 2, 3, right? Okay, let's check it out. So if I add these two vectors, I get 10/5. Add these two vectors, I get 15/5. Wow, I didn't make any mistakes. Look at that. It works.